All right, welcome back to AI Paper Podcast. Today we're diving into a really interesting paper on SkyReels V2. So for all you AI researchers and ML engineers listening, the big headline is this: SkyReels V2. It's an open source video generation model. And it's not just keeping up with closed source giants like Sora and Kling, it's actually hitting the top rank on VBench for publicly available models, well, as of February 2025 anyway, for video quality. Plus, it's got some neat innovations for making longer videos that you have more control over. If you just need the quick summary, maybe for a short clip, SkyReels V2, new open source video model, matches or even beats the closed source leaders on VBench quality. And it allows for longer, more controlled video by tackling issues like text alignment, motion quality, and, duration limits.
Exactly. And I think what's really striking for folks in the field is how it tackles these persistent headaches in open source video gen. The ones where your detailed prompt about a specific shot just doesn't quite land visually. Or the motion feels a bit off. Not quite high quality. And of course, the classic limitation. Most open models are stuck doing pretty short clips, like 5, maybe 10 seconds.
Right. And we generally see two main approaches, don't we? Diffusion models and autoregressive ones. Both have their pros, definitely, but they also have their drawbacks. Diffusion gives you amazing frames, super detailed, but sometimes stringing them together smoothly over time, that temporal fragmentation thing the paper talks about, that can be tricky.
It can. And then autoregressive models are often better at that time aspect, that consistency. But they can run into this problem where errors just kind of build up the longer the video gets.
So the goal for us today is really to unpack how SkyReels V2 tries to get around these problems. Looks like a pretty comprehensive strategy, right? Like they're hitting it from multiple angles.
Yeah, definitely. It seems to be a combination of really careful data processing, a new video captioning system they built, this multi-stage pre-training method, and then some cool post-training tricks like reinforcement learning and something they call diffusion forcing.
Okay, let's start at the beginning then. Data. The paper really hammers home how vital high-quality data is for these kinds of film-focused generative models. So what kind of data are we actually talking about here? Where did they get it all?
Right, the data pipeline is, well, it's massive. They pull from 3 main buckets. First, general stuff. Open source data sets you might know, like Qual36M, Human Vid, plus a load of video they crawled from the web. Second, and this scale is just wild. They built their own data set.
Yeah.
Over 280,000 films, 800,000 TV episodes from over 120 countries.
Wow.
Yeah, adds up to over 6.2 million hours of footage.
That's incredible.
And then third, they pull in high quality stuff from artistic repositories too. The raw video count is something like order of 100 million clips. Oh, and also important, they used a similar amount, about 100 million concept balance images for the early training phases.
Okay, 100 million scale raw input, that's a lot. So the immediate question for any ML engineer listening is, how do you make sure you're using the good stuff? How do you filter that?
That's where their progressive filtering strategy comes in. It's not just one filter, it's multi-stage, and the rules get tighter as the data moves along. But, and this is pretty key, I think, it's not all automated. They have human-in-the-loop validation at every major step.
At that scale?
Yeah. Checking data sources after shot segmentation, after pre-training, post-training, the whole way. They even set thresholds for bad case rates to keep the quality bar high. Honestly, having humans look at data at that scale just shows how serious they are about quality.
That must be a monumental effort. Okay, so they've got the sources, they've done this intense filtering. What's next in the prep?
Next is pre-processing. Several key things happen here. First, shot segmentation. They use tools like PyDetect, Transnet V2 to break down the long videos into individual shots, with the basic building blocks. Second, these shots get annotated using their hierarchical captioning system. We'll definitely get more into that. Then, more data filters, but the strictness varies depending on which training stage the data is headed for. And finally, they actually use data croppers to fix some quality issues within the videos themselves.
You mentioned subtitles and logos earlier. Those can really mess up a clean generation, right? How did they get rid of those without just chopping away half the useful picture?
Yeah, they have a pretty smart process for that. Starts with the black border crop using heuristics, just cleaning up the edges.
Yeah.
Then for subtitles, they look in the usual suspect areas, top, bottom, sides, using the CRC model. That's an OCR model.
Okay, CRFT for the text.
Exactly, to find the bounding boxes. For logos, they focus on the corners again, common spots, and use mini CPMO for detection. The clever bit is the cropping. They find the biggest rectangle inside all those detected boxes. And they only keep the shot if that cropped area is still, like, over 80% of the original frame, and the aspect ratio is similar. So they ditch the junk but keep most of the actual scene. Pretty careful data cleaning.
That does sound smart. Preserves the important visual info. And I saw they also mentioned data balancing, but later, in post-training, what's the idea there for ML models?
Right. In post-training, they do this concept balancing. It's based on the subject categories their captioner identifies. The main reason is to stop the model getting, fixated on just the most common stuff in that huge data set, like endless shots of people talking.
Makes sense. Avoids bias.
Exactly. It actually cuts the data volume down quite a bit, maybe 50%. But the result is a more even mix of concepts. Figure 5 in the paper shows it well, like balancing out human shots with things like scenery or animal. Table 2 gives more detail on subtypes. This rebalancing just helps the model build a broader understanding and generate more varied stuff.
Okay, so we've got this massive, cleaned, high-quality, balanced data set. Huge effort. Now, how does the model understand what's in those videos? That brings us to their video captioner, SkyCaptioner V1, right?
Precisely. SkyCaptioner V1's job is basically to create super accurate, detailed video captions. It uses structured formats and these things they call sub-expert captioners. Key goals are fixing errors MLLMs might make, getting better at describing dynamic shots, expressions, camera moves, and even tweaking caption detail for text to video versus image to video.
This structural caption sounds like way more than just a cat sits on a map. Looking at figure 6, what kind of details are we talking about?
Yeah, it's really comprehensive. You've got detailed info on subjects, main ones, secondary ones, their attributes, even hierarchical types like animal, mammal. It covers their appearance, actions, expressions, where they are in the frame. Then there's shot metadata. That's things like shot type close-up, medium, long, shot angle, eye level, high, low, position front, back, side, plus camera motion, the environment, the lighting. It's a lot. They start with a powerful base model, Qwen 2.5 VL72B Instruct, to get an initial draft. But the real trick is using outputs from specialized sub-expert captioners to refine those descriptions. That boosts the accuracy on specific details.
And how do they actually use these super detailed captions for different tasks, like text to video or animating an image?
They use something called Caption Fusion. For text to video, you want dense, detailed captions. Give the model lots of instruction.
Right.
For image to video, it's more focused. Key subject from the image, plus the desired action or expression over time, and the camera move you want. Interestingly, they also randomly drop about 10% of each field during training.
Why do that?
Makes the model more robust, so it can still work, even if the user doesn't provide every single tiny detail in their prompt. Appendix C has the nitty-gritty on the fusion.
These sub-expert captioners sound crucial for getting that really granular detail, especially on the film language side. Tell us more about those. What do they specialize in?
Absolutely, they're key. They build individual models trained as experts on specific things. First is the shot captioner. Its job is classifying shot type, close-up, etc., shot angle, eye high, low, and shot position, back, front view. They trained it in 2 phases. Baseline on web images first, for general understanding, then fine-tuning on balanced real film data, about 2K samples per category, to get really precise on those classifications. And the results are pretty good. Over 82% accuracy for type, nearly 79% for angle, and over 93% for position. That's a solid grasp of framing.
Those are strong numbers. What else do these sub-experts focus on?
Next up is the expression captioner, all about faces. It describes the emotion label, happy, sad, neutral, the intensity, specific facial features involved, and even a temporal description, how the expression changes over the shot.
Temporal description too.
Nice. Yeah. Again, 2 phases. First, detect faces, classify the main emotion, then use a VLM intern VL 2.5, give the emotion label as a hint, and use chain of thought prompting to get it to generate a detailed description. They trained this on about 10K internal examples, got 85% accuracy on the emotion classifier, and the full captioner scored well on all aspects: emotion, intensity, features, temporal. Getting expressions right is so important for believability.
Definitely. And the last one tackles how the camera itself is moving.
Exactly right. The camera motion captioner. It uses a hierarchical approach. Starts with motion complexity, filtering basically, identifying static shots or really messy, irregular motion it can't easily classify. Filters those out. For shots with clearer single types of motion, it uses single type motion modeling. They break down movement into 6 degrees of freedom, XYZ translation, plus roll, pitch, yaw rotation. Each axis gets discretized. Negative, 0, positive direction, plus 3 speed levels. Gives a really granular way to describe pans, tilts, zooms, etc. Trained on manual and synthetic data. And they used active learning in a single-type motion data curation step to efficiently build up a large, high-quality data set. Evaluation scores look good across various motion types. It seems to reliably pick up on how the camera's behaving.
So all that rich detail from these specialized captionals gets combined into the main SkyCaptioner V1.
Precisely. SkyCaptioner V1 uses Qwen 2.5 VL7B instruct as its base. Then it's fine-tuned on about 2 million balanced videos, using the outputs from the base model plus all these sub-experts. And Table 3 shows it works. SkyCaptioner V1 gets the best average accuracy compared to baselines, especially on those shot-related details. A big step up in understanding cinematic language.
Okay, let's switch gears to the generation model itself. The paper talks about multi-stage pre-training. For the researchers and engineers listening, why break pre-training into stages like that?
The core idea is incremental learning. Build up the model's abilities step by step with increasingly complex data and high resolutions. They use the WAN 2.1 architecture as a base, but train the main part, the diffusion transformer or DIT, from scratch. Crucially though, they keep the pre-trained VAE that handles the frames and the text encoder from WAN 2.1. Saves a lot of work. And they use the flow matching framework for training. It's split into 3 main stages, going up in resolution, 256p, then 360p, finally 540p.
Can you break down what makes each stage different? What are they trying to achieve at each step?
Sure. Stage 1 at 256p is joint image and video training. Pretty strict filtering here, kicking out low quality or synthetic stuff. Goal is basic visual generation ability, learning fundamental concepts from a huge amount of data.
Okay, the foundation.
Right. Stage 2 bumps up to 360p, still joint image video. But the filtering gets much more sophisticated. They look at duration, motion quality, OCR presence, aesthetics, overall quality. You can see the output gets clearer, more coherent after this stage.
Getting refined.
Exactly. Stage 3 hits 540p, and it's video-only training now. Filtering is even stricter. They specifically remove user-generated content to focus on high-quality cinematic data. This stage really pushes for visual realism, better textures, finer details, more human realism, getting that cinematic look. Oh, and throughout this, they use a dual-axis bucketing framework to handle varying video lengths and aspect ratios efficiently, plus FPS normalization.
Makes sense. Build complexity gradually. So after all that pre-training, they have a post-training phase with even more stages. What's happening there?
Right, post-training is about further refinement, targeting specific capabilities. 4 stages, mostly at 540p, but the last one goes up to 720p. The sequence is high-quality supervised fine-tuning, SFT, then reinforcement learning, RL, then this new diffusion forcing training, and finally one more high-quality SFT, but at 720p. The first SFT at 540p uses that nice balanced data set to just tune up the overall performance and provide a good starting point for the next steps.
The reinforcement learning stage. That sounds interesting, especially for dynamics. What are they targeting with RL?
The RL stage is laser-focused on motion quality. They found initial models sometimes struggled with big, complex, or deformable motions. Stuff could look physically weird.
Yeah, that uncanny valley of motion.
Exactly. So they built a pipeline to get preference data, generate pairs of videos with slightly different motion, have humans pick the better, more realistic one.
Okay, human feedback loop again.
Yep. Then train a reward model on those preferences. Teach it what good motion looks like. Finally, use direct preference optimization, DPO, to fine-tune the generator using the reward model's feedback. Nudge it towards making more realistic fluid movements.
Okay, and then this diffusion forcing training. This sounds like the key piece for generating much longer videos, right? Maybe even infinitely long. How does that work technically?
It's a pretty novel training method for enabling long sequences. The core idea is, during training, each frame gets its own independent noise level.
Independent noise per frame, huh?
Yeah, sounds weird,
yeah.
But it lets the model learn to denoise parts of the sequence while considering the surrounding context. Then at inference time, it enables a kind of next frame prediction, a bit like autoregressive language models, generate new frames based on the last few.
Ah, okay, so it learns to predict forward.
Pretty much. They use specific schedulers for this FOPP during training, AD during inference. The AD scheduler lets it run synchronously or asynchronously, autoregressively for extending sequences. So yeah, diffusion forcing basically conditions future frames on the past ones, unlocking that potential for theoretically unlimited length. Though, as they point out, and it's important for anyone trying this, error accumulation can still bite you on really long sequences.
Good to know. And the final stage. Another supervised fine-tuning, but it's 720p. Why finish with that?
That last SFT at 720p, after diffusion forcing, uses that same high-quality balanced data. Its main job is simply upscaling. The previous stage is focused on motion, length. This one focuses on spatial resolution. Enhance the visual fidelity, sharpness, detail by treating the model to output at that higher 720p resolution. Polish the final look.
This whole pipeline is incredibly intricate. For our audience who actually builds and trains these things, what did they share about the infrastructure? Making this happen must need serious compute and optimization.
Oh, absolutely. They give some good details. For training optimization, big focus on memory saving. Things like operator fusion, gradient checkpointing with BF16 precision, standard but crucial techniques, also selective activation, offloading, moving stuff to system RAM. All vital for fitting these huge models.
Yeah, memory is always the bottleneck.
Totally. They also built an intelligent self-healing framework for stability. Detects node failures, isolates them, reallocates tasks, migrates things, keeps the training run going.
Essential for long training runs.
Definitely. And for parallelism.
Yeah.
Pre-compute the VA text encoder outputs, use fully sharded data parallelism, FSDP, for the main DIT model weights and optimizer states.
Yeah.
And at 720p, they added sequence parallelism for activations, really distributing the load.
Okay, what about making it usable? Inference optimization, getting those videos generated reasonably quickly.
For inference optimization, speed and efficiency were key. They targeted RTX 4090s, used VRAM optimization tricks like FP8 quantization, lower precision, less memory, parameter offloading again, letting them run 720p even on a single GPU, which is pretty cool.
FP8 is becoming more common now.
It is. They also specifically quantized attention and linear layers, using things like Sage At-N2 8-bit for more speedups. Multi-GPU helps too. They used content parallelism, CFG parallelism, VAE parallelism, got it to 1.8x speedup with 4 to 8 GPUs. And finally, distillation, using a technique called DMD. Train a smaller, faster student model to mimic the big teacher model, gets much faster generation times, lower cost.
Right. Distillation is powerful for deployment. Okay, so after all that, data, captioning, training, optimization, how good is SkyReels V2? How did they actually measure its performance?
They used a mix of subjective human evals and objective benchmarks, which is smart. They built their own benchmark, SkyReels Bench. Ken 20 text prompts, humans rated videos on a 1 to 5 scale across several dimensions, like instruction adherence, did it follow the prompt for motion, subject, shot type, expression, camera, no hallucinations. Motion quality dynamic, fluid, plausible. Consistency subject seen over time, first frame fidelity for I2V, and just basic visual quality, clarity, color, structure.
So detailed human feedback.
Very detailed. And the results showed SkyReels V2 made big strides in following prompt instructions compared to others, while keeping up on motion and consistency.
And the objective benchmark, VBench.
Yeah, they use VBench 1.0, the long prompt version. SkyReels V2 came out on top there too, beating other open models like CogVideoX, OpenSword 2.0, Hunyuan Video 1 2.114b, highest total score, highest quality score. Interestingly, its semantic score, how well it matches the prompt's meaning, was slightly behind 1 2.114b on VBench.
Any reason why?
The authors suggest VBench might not fully capture nuances in shot scenario adherence, which is where their human evil on SkyReels Bench showed V2 is stronger, so you kind of need both types of evaluation to get the full picture.
Makes sense. The paper also touches on applications. For the researchers and engineers listening, where might this model make waves?
Several cool areas. Story generation is a big one. That diffusion forcing opens doors for longer narratives from sequential prompts. Generating 30-second shots is a good proof of concept.
Right, potential for procedural content.
Definitely. Also, strong performance in image-to-video synthesis, animating static images well. Then there's Camera Director. They fine-tuned the I2V model specifically on camera motion data, got much better cinematographic effects, more fluid, diverse camera work, very useful for controlling the visual storytelling.
That sounds really useful.
And finally, Elements to Video Generation, E2V. This is a new task they propose with their SkyReels A2 framework. Lets you compose characters, objects, backgrounds using text prompts while keeping fidel to reference images for those elements. Super controllable generation. They even made a benchmark, A2 Bench, for it. Future plans mentioned include adding audio and pose control too, building on their SkyReels A1 work.
It really is impressive seeing an open source model hit this level, especially with that kind of controllability. Okay, as we wrap up our look at this paper, what are the main takeaways for our audience?
I think the key things that make SkyReels V2 stand out are: 1, that big improvement in prompt adherence, likely thanks to the sophisticated SkyCaptioner. 2, the significantly better video and motion quality coming from that whole meticulous multi-stage training process, the data work, the RL for motion, the resolution stages. And 3, definitely the diffusion forcing framework. Enabling much longer video generation is a major step, Even with the current caveats, it opens up a lot of possibilities.
And you mentioned a caveat, a current limitation with that diffusion forcing people should keep in mind.
Yeah, they're upfront about it. While it enables longer videos, error accumulation can still happen on very long sequences generated this way. They state future work will focus on tackling this, improving scalability and reliability for really extended generation without quality loss. So it's a known area for ongoing research.
Good to know. And it's always great to acknowledge the team behind such a big project. Does the paper mention the key people involved?
It does. Yahoo Zoo is listed as project sponsor, Gibbon Chen as project leader, and it acknowledges the teams working on infrastructure, data and captioning, and model training. Clearly a big collaborative effort.
Absolutely. So considering SkyReels V2's advancements and seeing open source models perform at this level, it really makes you think, doesn't it? What new creative avenues, what new technical applications might open up now, especially in areas like actual film production or maybe virtual experiences? And what does it mean for the field now that these incredibly powerful tools are becoming openly available? Definitely gives us all something to chew on.